Okay, the DriveToPose command. This is by far the most sophisticated subclass of command in 3061 lib. Um, Being able to have the robot automatically drive to a specified pose is really, really useful. We use this command um, all the time, almost every year that I can recall, to have the robot automatically align to something. It is commonly used to align to field elements for either collection or scoring. Um, it can be used to align to other points on the field for various operations. Um, and this command has been updated significantly in 2025 to provide more functionality that we found really that was needed in terms of automatic alignment to the reef in the 2025 game, and specifically branches within that reef. So there's a lot of documentation in this class because there's a lot going on here. But I'll talk through at least why there are these so many parameters to the constructor and how this is used um, for a very flexible drive to pose class that we continue to leverage for different needs in different games. Um, First up, so obviously the swerve drivetrain. Target pose supplier. We use the supplier of the pose and not just the pose itself because we found there are times where you may want to change the target pose as this command is executing. Um, Examples of that would be um, we wanted to support scoring when we are one coral width away from the reef because a coral had been dropped and rolled up against the reef there. And so we would on the fly change the target pose if we detected that we were stalled against a coral. We also use this feature when scoring in the barge in 2025, in that we wanted to make sure that our elevator holding the algae was fully extended before we got too close to the barge, or else we would try to push the algae up through the net, which would not work. And so we would change the target pose based on the height of the elevator. There's another example there too. But if you have no need for changing the target pose, then simply use an arrow function, a Java lambda, and have that not change. The X supplier, Y supplier, and theta supplier, these are bifunctions, and what they're going to be provided is documented up here, but they're given the current and target X position in the field frame, and they're expected to return the X velocity in the field frame. Often this is just handled by a PID controller, and we'll see an example of that shortly. But there are times we want this handled by something else. Um, you may want to fuse a PID controller along with a joystick input. So again, in 2025, when scoring at the barge, we wanted to specify the target pose and use a PID controller for the X and theta values, but we wanted the Y value to remain under the driver's control so that they could find an open spot on the barge on which to score the algae. Target tolerance is how we define the tolerance for, like, we are at the pose, we're close enough to consider this command finished. We have a Boolean, which if true finishes when at target is true, that means this command will finish when that tolerance is met. There are times we don't want this command to ever finish. We want it to be interrupted by something else. For example, we didn't want this command to finish when we were scoring in the barge. We wanted the command to be interrupted when the driver actually scored the algae in the barge after they were aligned properly. Pose difference consumer. This lets other logic run in other code in response to what is the difference between the current pose of the robot and the target pose of the robot. So for example, you could do things like adjust other subsystems, other mechanisms as you approach the target. At target consumer, which I skipped over, this is a consumer that just gets a Boolean. And so some other code elsewhere can know if the robot has reached the target within the specified tolerance. And then there's also a timeout. If the timeout expires, the command will end. Let's look at how you would construct one of these for some additional context, and then we'll go back and look at the three methods that make up DriveToPose. So here's a cross subsystems command factory, which we'll look at more later. I just want to focus on this one section here of get DriveToPose command, where we actually construct an example DriveToPose. Now, every year this would need to be different. This is just an example. And so what we're doing here is you can see that we're specifying different methods here for getting the target pose, the x, y, and theta velocities. And so if we look at those, get target pose will always return a pose with this specific pose here. It's not changing as the robot moves around the field. Our calculate x velocity is simply using a PID controller with tunable constants. Our y velocity, same thing, PID controller. Theta velocity, same thing, PID controller. But we could certainly replace one of these to use, for example, like the y value from the joystick or something instead, if we wanted to do that and fuse that with the DriveToPose command. Here's our tolerances for determining when we are close enough to be considered at the target. We do want to finish when we hit the target. We added a little consumer here of when we do reach the pose, so we will actually change the LED pattern from when we are auto driving to when we're at the pose to give feedback to the driver. If like you don't care about the pose difference consumer, we just have an empty consumer here, right? We just do nothing with that pose difference that was applicable here. You could have something where as you approach the target, the elevator is going up or down, for example. Would be one possibility there. So this is what it looks like to actually configure and construct a new DriveToPose object, and how all of those suppliers and consumers can be specified. Back in the DriveToPose object, when we initialize stuff, we do have this feature in our drivetrain to enable acceleration limiting, and so we always enable that while DriveToPose is executing to make sure that we don't tip the robot. And so again, that can be tuned from year to year, but it's there by default. We log some information that's really useful when you look at this later in Advantage Scope and you want to see the DriveToPose and did it finish and when was it within tolerance and all of that. So we log those values as well. We restart our timeout. And we keep track whether this is the first run. We'll see why that's important, meaning the first time the execute method is called for this particular scheduling of the DriveToPose command. This is where things will get interesting that I kind of glossed over earlier. So we get the target pose from the target pose supplier. We get the current pose from the drivetrain. And then we use the buy functions, the x, y, and theta ones, to determine what the new x, y, and theta velocities should be. So we do all of that. All of this occurs in the field frame. And what I mean by that is these poses are in the field coordinate system. And so when you look at the difference in the x values, these are the x values in the field coordinate system, not relative to the robot or the pose itself. But we found that to be effective and fine for supplying these values. They work particularly well when you fuse them with joystick inputs, because usually we're using our joysticks in a field relative fashion as well. We calculate the field relative difference here. So the difference between the target and the current for the X, Y, and the rotation. So we have that to use as well. But then we also calculate the pose difference in the target frame. And we do that by constructing a new transform 2D object. And you'll notice the parameters are called initial and last. But we want the order really matters. And we want the pose difference in the frame of reference of the target, not in the current frame of reference of the robot. And the reason for that is we've found over the years that some of the per direction adjustments we want to make are always relative to the coordinate system of where we're going to end up and not where we are now. We don't really care which way the direction the robot is facing at the moment. We care as we get closer to the target. So that is why we have target pose, comma current pose, despite the names of the parameters. This means that the difference will be in the frame of reference of the target. What can be a little misleading, for example, though, is that if you think like, oh, I still have 2 meters to go in the X direction, that would show up as -2 because again, it's in the target pose reference frame and the robot is like 2 meters behind where it's going to be. Um, so logging this, displaying it in Advantage Scope, sketching can all help make sense of the geometry involved. It can get a little confusing, but it is super, super useful. So all of the other stuff in DriveToPose operates in the frame of reference of the target, and that's where we get a lot of our cool features. So we take the velocities that have been calculated in the field frame, and we need to map those into the frame of the target, and we do that through this rotational transformation. So now we have the velocities in the target frame in terms of X, Y, and rotational. And then we have this adjust velocities method. This basically gives us the opportunity to adjust those velocities based on the current pose difference in the target frame and the velocities. So what this method does by default is just return the velocities unchanged. But this class, DriveToPose, could be extended, and this method could be overridden to adjust the velocities for some reason. So there have been times when we want to make sure that we drive into a field element to collect or to score, to make sure that we don't prematurely slow down. It's okay if we hit it at velocity. It might even square the robot up, which is great. And so we might override this method in a subclass and add additional velocity in the X direction to make sure we actually hit drive at velocity into the target pose and don't stop right at it, as an example. So that's the adjust velocities method. After we adjust the velocities, we need to convert them back to field relative velocities because that's how we're going to tell the robot how to drive. We deal with the alliance multiplier to deal with if we're on the red alliance, we need to negate those directions because the drive method assumes from the perspective of the driver in the driver station. So we handle that as well. And we log all sorts of information about that to help us tune this DriveToPose thing. Is finished. So for is finished, we pass along the current pose difference in the target frame to the consumer so that that code can do whatever it wants with it. We then call this method is pose within tolerance. By default, this method simply checks against the specified tolerance when the command was constructed and returns true or false based on that. This is a separate method, which again can also be overridden by a subclass if determining whether the pose is within tolerance has some special requirements. So for example, maybe there's an asymmetry. You want to make sure that it's okay to be farther away in the positive direction, but not as far away in the negative direction, as an example. Or there are other things you want to check. You could override this method in a subclass and do that as well. Based on what's returned from that, we pass it along to the at target consumer. Here's an important feature that we added in 2025. The first time the isFinish method is called, we invoke this method can reach target pose. And by default, it returns true. But you could override that method to determine if from where the robot currently is and where the target pose is, it may not be physically possible to get there from here. Because remember, drive to pose basically just drives, it drives in a straight line using the PID controllers. It does not have the ability to drive around things like field elements. And so you could override can reach target pose in a subclass. You could check for things like, oh, you're going to run through the reef if you try to get there from here, and return false, in which case we invoke this set drive to pose cancel method on the drivetrain, so that we don't try to do that, and we can alert the driver with a LED pattern, for example. So that's a useful feature there. Otherwise, we log a bunch of stuff, and then this command is considered done. It finishes when we're at target. Well, I'm sorry, it finishes when we're within tolerance if it was configured to finish when we are in fact within tolerance, or it might run forever. If we can't reach the target pose, it will also finish, or if the timeout has elapsed, it will also finish. Regardless of how it finishes, whether it's interrupted or not, we will disable acceleration limiting, we'll stop the drivetrain, and we'll log that information as we go. And these are the three methods that can be overridden in a subclass. So what makes DriveToPose so powerful is that there's a number of suppliers and consumers, which can lend itself to some very sophisticated functionality. And there's the three methods that can be overridden in a subclass for even additional functionality that can't be done through the suppliers and consumers.